Okay, well, then let's start. Hello once more. Today will be personal ThECS lecture. Then let's continue with our material. What we discussed previously. There was method of calculating such called complex electrical circles. It was here. That called the Kirchhoff's law, and just straight using of such Kirchhoff's law. We discussed that generally we have two types of circles. If in circle in our mathematical model we have only one source of energy, then it called simple, and we could calculate equivalent resistance of such circle, and the current near the generator will be the value of generator dividing on the total resistance. In all other cases, when we have couple of sources, more than two, starting from 2 and then 3, 4, 5, and so on, such circles, such models are called complex, and we cannot find total resistance because we don't know near which points we should do this, because near each of sources we could calculate total resistance. That means that mathematically we will have couple of values, and that is mean that we should use something else, some other approach. As such approaches, we have lots of methods, and we started from the direct application of Kirchhoff's law, but we discussed that it should be the most complicated in terms of number of mathematical equations, the most complicated methods, because the matrix formed from formulas from equation will be in the highest dimension. For example, if we have some circle with 4 sources, 6 consumers, it topologically consists of 3 meshes, 3 internal circles, and in such system we will have 6 equations to find the currents, because in each branch we have the specified current, and the total number of equations will be 6. It is quite high, because if we will use matrix form of solving such system, the matrix will be in the dimension 6 on 6, 6 rows and 6 columns. And in computers that's okay, but if we want to deal with, for example, engineering calculator, it will be quite complex calculation. And in any case, this system is quite simple, only 3 meshes. But what will be if we have, for example, 20 meshes or 100 meshes, quite widespread energetical systems with lots of consumers, lots of generators, how we could simplify in this case. Then, for this purpose, the general method little bit transformed, and was proposed couple of variations as called mesh current, node analysis method, and couple others. Generally, in the most general case, if we didn't speak about something specific, generally these two are the most common used, and they are just transformations of unknown variables. They are just using substitution of variables to sum another one. And such substitution makes decrease the number of our equation. It is the main idea. How it works, let's discuss. For example, here, this is the example from the previous time, from the previous class. For this circle, less we obtain 6 equations, but we obtain these 6 equations because we have 6 different currents. As we see in current equation, different variables are 6 by number. And if we somehow will substitute these 6 unknown variables to decrease their number, we could decrease the number of general system of equation as we obtain as a result. And the proposition is to make some imaginary variable, because the real current, it is the real current inside the branch. It is the current that we could measure using the ampere meter and the answer that we are searching for. But if we will assume some imaginary value, such called mesh current, that some current flow inside mesh, inside all branches that are inside our mesh. And the same for each mesh, inside each own mesh current. For example, we could point it with some additional index, for example, M as mesh current, IM1, IM2, and IM3. Then the real currents that that flows inside the branch, inside branches in our circle, could be just obtained as a result of superposition of such mesh currents. The real values, for example, I1 in the first branch, here it is. It should be just the same mesh current because anything else flows through this branch. Such I1 should equal only IM1. Then the second current, I2, as we see, also should equal only such mesh current 2. Then current number 3, here it is, the direction. And if we will compare the real current with our imaginary currents after the substitution, it should equal the same direction IM2 and the opposite direction IM1, as we see just looking on the arrows. And I3, real current, should equal IM1 with minus and plus IM2. Then we could make the same movement for all other currents. For example, I4, as we look on the central branch and the direction, should equal IM2 with minus and IM3 with plus. And for example, let's try by your own for I5. If I5 flows here on this direction of arrow, how do you think? Which combinations of IM it will be on this picture?
Maybe IM1 minus, no, sorry. IM1 is in the top, right?
Yeah, IM1 at the top and IM3 at the right.
Okay, so the first is IM2.
Yes.
No, there's no. It's
yeah,
none.
yeah.
Sorry.
I just erased it. IM2, IM1, IM3.
Okay, and so I5 equal to minus IM1. Plus IM3.
Yes. Yes, you are right. Perfect. Yes, you get the idea. That is good. Then the I6 just will be IM3 with minus because I6 on the picture is flow up because the currents are pointed at the picture with some specific directions. If you don't have the directions of current, you could put these directions as you want. You could choose them by yourself. But according to this picture, we obtain such situation. And if we could substitute all our 6 currents, all our 6 unknown variables as some imaginary variables after substitution, then we see that these imaginary variables only 3 by number. And instead of 6 unknown, we could search only for 3. That is mean instead of 6 equations, we could search only for 3. Only we could make system consist only of 3 equations. And it is twice simplify our system. But generally, this transformation grounding only on substitution of variables. Just substitute the real one by using some imaginary. How our system should looks like, let's see here. I will erase currents and we'll use this space to write the system. Let it be here. We are writing the same Kirchhoff law. We are writing for each mesh, just total voltage of consumers equal total voltage of source. Then the mesh current IM, it influences all resistances. As we see, all 3 resistances inside this mesh, R1, R3, and R5. According to our initial picture, initial drawing. Then also inside this first mesh, inside this blue mesh, also green current influence on R3, and the direction of we takes the internal mesh as the main and always with plus, and all other depending on the direction compared with the mesh of circle that we're looking on. If we have circle number 1, mesh number 1, blue current will be always with plus, all other will be compared with this blue by the direction. As we see on the arrow green one is opposite directed, and red one is also opposite directed. That is why they will be with minus. And they inflow only on the resistors that are inside this blue circle. That is mean we should write IM2 on R3 and minus IM3 on R5 should equals sources inside this mesh. We have source number E1, electromotive force, and it is the same directed at the direction of mesh current. That is why it is taken with plus. And this is the equation that we get. If we will transform this equation grouping near the resistors, we could obtain such thing. IM1 R1 plus IM1 minus IM2 on the R3, then plus IM1 minus IM3 on the R5. Equals E1. And what does it mean IM1 minus IM2? It is just the current number first minus second. It is just current number 3, but depending on the direction as we write it here. If we write in first minus second, it will be minus I3, the real current. I want to show that this equation that we obtain in mesh currents will be the same Kirchhoff equation that we was writing last time in the real currents. Just the same equation, but written in the different unknown variables. Because here will be minus I3, as I wrote, multiplying the resistor. Sorry, just one moment. Yeah. And what does it mean IM1 minus IM3? It is current number 5. Current number 5 with opposite sign. Instead of this, because that is the dependence that we wrote at the beginning of the lecture, as we try to compare these unknown variables, real and imaginary. It will be with minus I5. And as we see, it is the same, and IM1, the same current, just I1, because in the upper branch, we don't have any other current. And as you see, we rewrite the Kirchhoff equation in general form as we did it previously, last time, in the terms of mesh currents. That is mean it is the same equation, and we could make this movement, this operation, for each mesh inside our circle. For example, if we write the same equation for mesh number 2, it should be mesh current second with plus, because the main mesh always with plus, on both of resistors, all 3 resistors that include this circle, R2 plus R3 plus R4. and other two meshes, they are opposite directed. It should be minus IM1 with the resistor number 3 and IM3 also with minus with the resistor number 4, because these two meshes have the same resistor 4, and it equals the sources inside it. The second will be with plus because it is the same directed, and the source number 4 will be with minus because of opposite directed. It is the idea how we get this equation. We will obtain the system of 3, and let's try all together the equation number 3. How do you think? According to this idea, what should we write starting from the red mesh? How it will look like here? Do you hear me?
Yeah, sorry.
Yeah. No. Yeah, just let's try together.
Yeah, okay. I just wonder the E6 direction. I can't see.
Okay. 4, 6, and 5. The upper
I know.
resistor is 5.
I see E6, E.
Sorry, just one
As a
moment.
circle? Can you understand me? Okay.
Yeah, sorry, just one small moment.
Okay, maybe I can.
Yeah.
Let me try.
I'm listening.
Let me try.
Okay. Yeah.
Maybe plus IM3 and multiply R4 plus R6 plus what? R5. Thanks.
Yeah, R5. Yeah, because I draw on the name of index that I understand that you don't see it. R5. Okay, then.
And then minus IM1 multiply R5.
Yes.
And then minus IM2. Oh no. Plus IM2. Plus IM2 multiply R4.
R4. And first guess was right because the direction is opposite. The arrow, down, and other arrow is up.
It's up. Okay.
Then, then with minus. Okay, perfect. And yeah, you get the idea. That's good. Then.
Thank you.
Welcome. And sorry, the last point about sources. We have also two sources
E4,
here.
E4 minus E6.
Yeah, perfect. E4 minus E6. Then, as we see, we have only 3 unknown variables that we could solve this system. And as a result, we will obtain our IM1, IM2, and IM3, all these mesh currents. And instead of system like here, 6 equation, we could use twice simpler system only with 3 of them. And it is on the widespread system with lots of elements, it is quite useful thing, because instead, for example, of 100 or 1000 equations, you could simplify system, for example, twice or 3 times. In engineering terms, it is very good result. Then after we find these mesh currents, we could find the real currents as we did at the beginning of our practice. It is just a comparison of these two approaches, starting from the previous topic last time. Here we have a couple of examples in the chapter discussing just this method, mesh current method, or just mesh method. Couple of examples how we are doing it. If we have only 2 meshes, then instead of Kirchhoff's law 3 equations, because 3 branch with 3 currents, we could find the system of 2 equations instead of 3, only 2, using mesh currents. Here is, instead of letter M, we have double index. Instead of IM1, just I11. Instead of IM2, just I22. It just depending on book or on author. You could find any of these pointing, or with double index or with letter M. Then algorithm, how we are doing it, what we try to do practically. The signs plus or minus you are choosing on the direction of mesh current. First of all, how the algorithm is. The first step, you are choosing the direction of mesh. Generally, you could choose any direction. Mostly, the choice is clockwise direction, but it isn't some straight mathematical restriction. You could choose any direction as you want. But after you choose the mesh directions, all other signs plus or minus you are taking compared with these directions. Sources compared with these directions, real currents compared with these directions, and in the branch combined with both of these currents, also you compare these directions, are they similar or opposite. Then first step, choosing direction. Second step, writing the system of equation as we did previously, and from this system finding mesh currents I11, I22. And the last step, you are looking for real currents starting from the imaginary, starting from the mesh currents. As it did here, the general form of equation with some combination of resistors. It could be positive or negative, and some combination of sources. Also could be positive and negative. As for me personally, I like better not such general form that we are writing equation and looking for coefficients R and E, but just write the real view as it looks like. Not in general form when we assume that some coefficient R11 equals from something, some coefficient E11 equals from something. I like just write the general, the real form depending on the circle, and not to move to general form. You could do as you want, or starting from general form and determine the coefficient, or just write only a real form for the view of the circle, substituting these coefficients inside the equations. And after you wrote these equations, after this task in numbers, 2 electromotive force, this example in numbers, 2 electromotive force, 3 resistors, obtaining a system in mesh currents, substituting value of resistances and electromotive forces. As a result, finding 2 mesh current, I11 and I22, and after it, finding the real one. If you will compare the mesh currents that was chosen here, just one moment. And the real current that inside our circle, mesh current I11, the similar with I1, depending which direction will be. For some reason in this picture, the direction of current I1 is chosen opposite the source. That is mean if in the initial data this direction is chosen opposite, then we are taking I11 with minus. Then I22 also opposite with minus, and the central branch equals first mesh current minus second mesh current. And we obtain positive currents in milliamperes, 133, 429, and 286. And we could check the Kirchhoff law to check if we find this solution correctly. 2 currents in left and right branch altogether should equal, or the sum of all 3 currents should equal 0, or depending on the direction. We have inflow current I2, outflow current I3 and R1. That is mean that if we add I1 plus I3, we should get current I2. And if we, as we see, this Kirchhoff law is true, and that is mean that we find everything correctly. Just such steps that we discussed, we implement in our solution. Choose the direction, then write system of mesh current equations. The second step, write system with mesh current equations, substitute numbers from initial data, and obtain the solution as mesh currents. The last step, using mesh currents, taking the real currents I. And after it, we could check, for example, using power balance equation, that power generates by these 2 sources should equals power consumed by 3 resistors. 3 resistors consumes joule heating, then it mean I square R square of current on resistivity. Substituting our solution, obtain about 7 watts of power. And the same doing for the sources. As we see current inflow in the first case, the opposite direction, that is mean that power of the source will be negative. This source also works as a consumer. But the second current flows the same direction as the source. It should be taken positive, and you obtain, as a result, also almost 7 watt. These 2 numbers are equal, and that is mean that power balance also is true for our calculation. And generally, you may ask, how do we know these current directions? or we should choose them by ourselves. It depends from initial data. If in the circular model you have the concrete direction of current, you just taking as it given to you. If you don't have direction, if you have, for example, current circle without any directions, for example, in some in some circle, maybe some circle without any directions, okay? Because generally you could have more, for example, here, you have some drawing without any current direction. That is mean that you could choose any direction as you want. You could choose current direction, for example, like this, or for some reason you could choose the opposite direction. Mathematically, it doesn't matter. If your guess is correct, you will obtain positive current. If your guess is incorrect, you will get negative current. But mathematically, this is nice answer. This is correct answer, because even negative answer will give you the concrete direction and the concrete number of current. That is mean you could make any guess about directions and obtain numbers after the solution. You shouldn't change the direction. You just take in your positive or negative answer and it will be true. If you have the direction inside your initial data, then you are taking this direction. That's all. Also, some restriction of the method. As any mathematical approach, this method have some restrictions. The restriction is connected to the current source. If you have some current source inside your model, you should choose one of the mesh equal to this current source. In any case, you should equalize this mesh current number 4 to the value of current source J, and then doing the same operations. It has positive moment because such point decrease the number of your equation, because if you have 4 meshes, but one of the mesh should be equal to the current source, then it means that this mesh is already known. Then you have only 3 unknown variables in other parts of the circle. And you should look only for other 3, I11, I22, and I33. Such restriction. Also, okay, we don't have it inside model, but I will show you here. Let's assume that we have current source inside our circle. Let it be some current source J here. What should we do? Because we have first mesh that flow through this circle, or let's take it as previous, for example, red color, through this source. And also we have second mesh that also flow through this source. Which mesh should we equalize to the value of source? Because we cannot equalize both of these meshes. That is other moment, other restriction, how we should use this method. We could equalize any of these current, or first or second, as you want. But if we are assuming first equals to J One moment. Equals to j. Then we cannot choose the second also through the j. We could choose the second moving outside the j. That j shouldn't be inside the second mesh that we are calculating. Or second variant, if in second variant we are equalizing I2 to j, then we should choose the first mesh as the outside circle, because j shouldn't be inside equations that we are calculating for some circle. For example, in this case, let's make picture, screenshot, and then using it on the previous solution. Let's compare previous solution, this one, both equations, with the new solution. We cannot use equation for solving that j will be inside it. That is mean that if we want to write the new system, it will be I11 that multiply on all other resistors. It will be R1 plus R2. Then we have blue mesh that also flow through the R2. It flows on the same direction. That is mean that it will be positive. It should be plus I2 on R2 equals the source that we have in this circle. It equals E1 minus E2. And what's about second circle? The second mesh current I22 double index should equals just j. Instead of these two equations, we obtain this pair. One of them already solved because j is a constant, it is a number. And we should find only unknown current I11. If we have current source j, it decrease number of unknown variable on 1. And if in the initial circle we have 2 unknown variable, that with including j, it will be only 1 unknown variable, only from this equation. Such specific thing. All equations for solution we should take outside as mesh outside the j. You could ask, could we do the same in this circle? Could we, for example, take first mesh like here and second mesh like here, instead of what we did previously? Yes, of course, it haven't any restriction. We could take mesh, for example, like here. The only one point that in new mesh should be at least one additional branch compared with the previous one. For example, if in blue mesh we have branch number 2 and branch number 3, then while we choosing the red one, at least one branch should be new. Or if we are taking internal mesh, we are adding the new branch, or we are taking the outside mesh. Also, we are including additional branch. Why generally, if with absence of current source, we are taking internal mesh? Because the view of equation will be simpler. Because if you are taking internal mesh, the number of resistance will be less. Let's just compare for some complex circle. For example, here, if you will take internal mesh, the number just almost the same, but okay, let's do like this. 3 internal meshes with 3 resistors inside them. But instead of green, you could take any other. You could take or outside because the new branch is added. Or you could take such mesh. Also, you are adding new branch that everything is okay. It is just how it's more comfortable for you. And for example, if you will take the bigger circle, you have 5 resistors inside it. First, second, 4 resistors. Just increasing the number of elements, the number of constants inside the equation. That is why if we don't have current source, generally we are taking only internal meshes, but if we want, we could take also external. But if we have some current source inside our circle, then we could take at least one external mesh just to neglect, just to make this constant disappear from the equation that we want to solve, because it is an additional unknown variable. And if we, for example, if we have current source and try to take couple of meshes using this current source, just our equation will be incorrect, just will be mistake inside our system, because or we should equalize both of these meshes to the source, but it will be incorrect because they are different. Or if we equalize only one, then we didn't take in account, don't take in account this source into the second equation, and it will be also the mistake. That is why in such case, only one correct solution, we should take the outside circle. Couple of slides moment in our mesh current method. Example like this. 2 examples. If we want, we could practice. I propose for today, I will tell something further about lecture material, but comparing with practice, I think you will train such things with teacher Ludmila, and also you could see in this methodical book about practice some moment about practicing mesh current method. I think where it is, linear DC circles. Let's choose some task. Using Kirchhoff's law, method of application Kirchhoff's law. Oh, for example, here, starting from the page number 12, you see the practical task with solution using mesh current method, and you could train this idea by yourself, just taking task number 114, try to solve, take task number 115, try to solve, and so on and so on. If you are doing everything okay, then perfect. You understand this method completely. If you will have some questions, please welcome, you could ask. I think teacher Ludmila also will send you some practical questions by training by yourself at home, just as a home task. And also you could train this method with her. If you will have any questions, please welcome, you could ask. Maybe
Okay,
some question. Okay, yeah.
And
okay.
you send these materials to me already or not?
I think I already sent some materials. I will check. Just one moment.
Okay, maybe I forget it.
No problem. Because there are lots of students, I'm also not sure for which group I send it. Just here it is. Yeah. Okay, I see on the email I didn't send them, then I will send it now.
Okay.
Yeah, from the September. Just one moment. The conspect of lectures and the book with problems. For now, that's all. Maybe something additional we'll send further. Yeah, they should be sent. Okay. For now, maybe you want to discuss something, maybe more detail, or everything okay?
It's okay, so clear. Thanks.
Okay, welcome. Glad to hear it. Then I think for node analysis method, let's discuss the next time, because in some terms, the mathematic is the same. We are making substitution of currents, but not in terms of mesh currents, but in terms of voltage, in terms of potentials. And not to make mix of information inside our head, I think we will do it next time. But today I will show a couple of useful things in other point of our discipline. Just we'll show the main idea and then move into the further material. Here it is. The method that will be next time for mesh current, as we see, we're making substitution of real currents as some meshes, and instead of real system, instead of real system, obtaining mesh current system. In the potential method, we are doing almost the same, real currents that we have, substituting in terms of potentials, in terms of voltages. And as the result, obtaining some system in voltages. Let's see some practical example. For example, here. We are obtaining system of equation, not in current, but in voltages, and looking not at mesh currents, but such called node potentials, potentials of the system. But the idea is the same, the substitution of variables. It will be next time. For today, what could be added? What could be added? Let's move a little bit further for the next material and a couple useful things about transformation, about simplifying their resistivities. Yeah, simplifying the resistivities, such called star-delta connection. As we return, if we will return to transformation of resistors, previous lectures, and which we discussed series connection, and adding resistances, and parallel connection, adding conductivities, or in general formula, adding the opposite value of resistances. Then we also have other form of transformations that, for example, not so obviously could be found, but they are also true for the circle. They called star-delta connection or star-delta transformation or PT transformation. It is the same. It depending which literature are you using. If you have a couple of resistors, the starting is here. Star-delta transformation, it looks like here. If you have 3 resistors that have the same point of connection, single point for all 3 of them, it looks like star. Then in Ukrainian-speaking literature, it also called star. But in the same term, if you will connect 2 wires for one of the resistor, just connecting 2 wires, it doesn't influence on anything, because this potential one will be through all this connector, through all this conductor, because on the metal, on the conductor, the potential, it is equipotential surface. The potential should be equal on all points. Then, or you have wire with 0 connection, the resistivity of such wire equals 0. Or you have only one point of connection without wire. It is the same combination of resistance. On the form, it's sometimes called T network. On the form, it's sometimes called star network. Also, it's sometimes called Y network. If you will look on this picture as a letter Y from the English alphabet, it's sometimes called Y network. It is 3 the same names of the same type of connection. And the second type, first type and second type. And the second type, just one by one, these resistors connected all together. For each pair of resistors have one similar point between each other, but not there is any single point for all of them 3, for 3 of them. Only pairs of 3 pairs of connection. It could be named as delta connection because it looks like Greek letter delta. It could be called P network because looks like letter P from the Greek alphabet. The same idea. If you will connect points with a single wire with zero resistivity, the potential will be the same. The potential number 3 will be in all points. Then physically, this triangle is exactly looks like at this square because there is no resistor on the bottom part, and that is why there is no voltage drop. It is the same potential. That is why sometimes it's called triangle. P network, delta network, or triangle network, 3 different names of the same type of connection. In Ukrainian speaking literature, the most common naming is star triangle network. Transformation star to triangle, triangle to star. In English speaking literature, it is mostly called or delta connection, Y delta connection. Or in electronical books connecting to electronics, it is called T network, P network, because it discusses as the movement of signal, as the flowing of signal. Some signal flows inside, some signal flows outside the system. And it looks like T or P network. But generally, it is exactly the same type of connection, 3 different names. You could call it any name as you want, any type of name as you want. I think teacher Ludmila will say on practice or star triangle or Y delta connection. Okay. Then what we could ask, what we could discuss about it, that we could substitute any delta by star or any star by delta. Instead, as we did, for example, in circle with series connection. Just one moment. Yeah. As we did, for example, where it is? Here. Instead of 4 resistor, substitute 1. Instead of 4 resistors, substituting 1 and simplify our circle. The same idea for Y delta connection. Instead of any, just one moment. Instead of any star, we could connect delta. Instead of any delta, we could connect star. In which situation it is useful? For example, here, we have simple circle, and theoretically, we could find total resistivity near the source. Because only one source, we discussed that it is called a simple circle, and we could find total resistivity of all elements. But these elements are connected in mixed type because we cannot divide them only on series and parallel, because series connection should be the same current, but as we see, currents will be different in all branches. Also, parallel should have the same voltage, but as we see, voltage also differs because different potentials, A, B, C, D, all values are different. For example, in case like this, if we don't have resistor number 8, it will be much simpler. For example, in this case, we could transform two resistors in parallel, then two resistors in parallel, then series of these pairs, just serial one by one. But what should we do in this case if we have a resistor in central branch? Because such type isn't parallel, isn't serial. And specifically in this case, it's quite useful to use a star delta connection, because here we have lots of such types. We have, for example, at least one star here with central point. Also, we see one star here with central point. Also, you have star here with central point. And you could take any of these three stars for transformations. For example, in this, for here example, author use the opposite transformation, not from star to delta, but from delta to star. Also, you have couple of deltas here. You have at least first delta here and second delta here. And or you could do this task in lots of variants, at least 5 different variants of solution. Generally, the most common is used delta to star, because when you are doing delta to star transformation, you are decreasing number of mesh by one, sorry. If you look on this type of connection, how many mesh do you have? You have 3 meshes, 1, 2, 3. If you will make delta star transformation instead of delta, substituting star, like it's shown here, substituting star instead of delta. Then how many mesh do you have? You have only 2 meshes, 1 and 2. That is mean you decrease the number of your equation and simplify the system. That is why in most cases you are using delta to star connection, because it decreases the number of meshes. But in some specific case, could be useful the opposite transformation. It's not a problem, because sometimes you also need it and you could use opposite transformation. For example, in this task, let's see how it is done by transforming delta to star. The first step, instead of delta inside circle, we have all resistances, 10, 20, 26, 18, 8, and 14 ohms. And we also have electromotive force 20 volts. Then instead of resistance 20, 18, and 8, we should substitute in some star with values of 7.8, 3.1, and 3.5 number of resistivities. And the currents will be the same. What is the criteria that our transformation is equivalent? That is mean all currents inside initial circle should equals all currents in the new circle. If we will get the same values of pink currents that don't take part in our transformation, then our transformation is correct, is valid. The current inside transformation could be different. For example, currents in this delta differs from the current inside this star. It is normal thing, they shouldn't be equal. But all other currents in outside part of the circle, they should be exactly equal, and it is their restriction, it is their criteria of equality between these two transformations. Why we take exactly these numbers? There is some formulas how we could calculate, how we could redraw this transformation. If we are transforming delta to star in the straight way, we should take, if we searching for branch of the triangle, of branch of the star, this one, we should take two branches of triangle that is near this node, multiply them, and divide by all three branches, by the sum of all three branches. In upper part, we are obtaining ohms in square. In bottom part, we are obtaining ohms. Ohms in square divided by ohms equals ohms. And the dimension of our equation is true, and everything is okay. Then we are doing the same for other branches. If we are searching for second one, we are taking two nearest branch of triangle to this one, multiply them, and divide on the same bottom part. And for the last one, the same idea. If we are making the opposite transformation in the opposite direction, and we are searching for some branch of triangle, we should take both branches near these points, add them, then multiply them in upper part, and divide on the last third resistivity. There is a mathematical improvement of these formulas. I will show it to you just now, but as a result, the formulas are like that. You could write them on some notebook just to have them near yourself, or you could make screenshot from the conspect, or you could search through the conspect to find them. In any case, for this transformation, they are valid. And you could use this transformation in any time. How these formulas could be approved? Just to check that they are valid. If these transformations called equivalent, then it means that resistivity should be the same. If you are connecting some measurement device, some ohm meter, to the same points, the ohm meter should show you the same value. If it shows you, for example, 100 ohms in first case, it should show you the same 100 ohm in the second case. How this ohm meter works? It puts some small voltage to make some small current and measure the resistivity of the object. If this triangle or this star is disconnected in the circle, just some combinations of resistivities that, for example, lie on the table without any electrical connection. That what you will get. This ohm meter will measure R12 parallel to serial connection 3.1 and 2.3. It will be R12 multiply on R31 plus R23 and divide on the R12 plus R31 plus R23. The formula of parallel connection. What it will show you on the right part. It will be just serial connection of two elements, because if these points are disconnected, the resistor number 3 just lay on the table without any connection to other part. The current will flow only through the resistor 1 and resistor 2. These values should be equal, and it will be like here. And you could make the same mathematical calculation on the other two types of connection. Now we connect ohmmeter to point 1 and 2, but also you could connect the same measurement device to points 2, 3 and to points 1, 3. And you will get the same formulas. After you transformating these formulas, you will obtain this one. For example, as you look here, R01 should be this part of the formula. Here it is. And R02 should be this part of the formula. Here it is. If you will add them, you will obtain the initial one. But initial formula we will get just from the basic physical ideas, just from the general physics. And after,
excuse
yeah,
me.
Yeah, of course.
I don't kind of understand why these two formulas are equal.
Why they should be equal?
Yeah.
Because it is idea of equality. The idea you are taking two equivalent circles. Inside one of them, just one moment. Inside one circle, you should have triangle. Inside second circle, you should have star. But these two circles should be exactly the same. They should be just the same circle. And your goal, your final task, to find which triangle you should connect here and which star you should connect here. Then circles will be the same. How it could be found? Just imagine that you are taking this star and triangle as separate parts of the circle. You are taking this triangle without any additional connections, without any other values, just a single star. Try to connect voltage source to it. For example, you are connecting electromotive force E. What will be the result? The current from this electromotive force will flow to the point of connection, and then this current will divide on two directions, and then will move next to the negative point of the circle. Yeah, everything okay for this drawing?
Yeah, okay.
Okay, and you are doing exactly the same for the star. You are disconnecting it from the circle, without any additional elements, without any additional currents, the idea that total resistivity should be the same. And you are connecting voltage source, electromotive force, to this part of the circle, to this star. How current will flow? It will flow through the resistivity. Then this is the point number 3 is open circle. It is disconnected. That current will not flow this resistor because there is no path for current flow. The current will flow only for resistor number 2. It will be the path of current flowing. And if we try to write the total resistivity of this system, what we have at the right? At the right, we have combination of 2 serial resistances, R1 plus R2. At the left, we have combination of parallels, like here, with plus. But if triangle equal to star and star equal to triangle, the current should be the same. The current in the first case should exactly equal the current to the second case. But if sources are equal, that is mean that resistivity also should be equal, that obtain the same current. Then that is why these resistivities should be equal.
Okay,
that is why. Okay, perfect. Maybe something else.
No.
Okay. It's the best way, the best advantage of personal classes when only one student is present, that you could ask everything that you're interested in. We don't have any other time restrictions. Okay. Okay. Then what the final conclusions from this lecture? What should we remember? The first conclusion, that we will speak about new method, the new method that is called mesh analyte method, or just mesh method. And the idea to make substitution of real unknown variables by some imaginary unknown variables as mesh currents. It will decrease the number of equations and makes opportunity to solve the system in more easy way. And the second part will be was about equivalent transformation. Additionally to serial and parallel connection, we have a new type that called star delta connection. For this transformation, we have specific formulas. And if we have, for example, resistivities of delta, we could find resistivities of star. Or if we have resistivities of star, we could find resistivities of delta. On the practical example, we have at the initial data resistivities of delta, substituting them in formula like here, delta to star, and obtain the resistivities of a new star. And how we could check? The resistivities of star should be always less than resistivities of triangle. You could just compare the number and see that they less. I think for today it's enough, lots of information. Next time we will start from this point and speak about couple other examples of star delta connection. We'll discuss till the end how this task is solved, and we'll return to some additional method for circle calculation compared with the nodal voltages, with the potentials. It will be next time. For today, that's all. For today, thank you for your attention and wish you a nice day and see you next time.
Okay, thanks. Have a nice day. Goodbye.
Thank you. Goodbye. Goodbye.